Hello, everyone. Uh, my name is Jorge Romero. I am a PhD candidate at Oregon State University, and the PIs for this project that's titled Simulating Earthquake and Tsunami Impacts on Open-Type Wharfs are Dr. Andre Barbosa and Dr. Claudia Rice. So this is an outline of what we will be looking at today. We'll go over some of the background, the objectives. We'll talk a bit about hazards and demands and the workflow I'm using. Here we are going to talk about how we are leveraging some very useful data generated by the Cascadia Coastlines and Peoples project. I want to emphasize on that. So I also want to mention our physical and numerical modeling, a validation, an application example, and for the end, I'll summarize and talk about our future and ongoing work. So to give you an important fact of how big the contribution to the national economy are for ports in the U.S., it's basically 1/4 of the national economy. That sums up to $4.6 trillion. So it's a pretty big number. So if we want to focus into the West Coast, we know that California has 12 main ports, and for these 12 main ports, they basically manage more than 50% of imports and exports for the U.S. And when we talk about Washington State, and we know that there's 26 ports along the Columbia River and Astoria, and for Oregon, we have 23 ports. To give us a comparison between one large port, as an example, the Port of Oakland in California, it compares to the to the economy of all the ports through the Columbia River from Washington and Oregon. So all of the ports from California, from Oregon and Washington, basically contribute the same as the Port of Oakland. Yes, California takes it all. So, what raised the awareness of the cascading seismic and tsunami events? Back in 2011, during the Tohoku earthquake and tsunami, they noticed some very large damage to coastal infrastructure. As you can see in the picture on the left, left. There's a very damaged medium-sized or large-sized infrastructure. You can see all those slabs burst up. We cannot tell with a certainty that either the earthquake or the tsunami damaged this. We could only say that it's a combination of both. We also saw some very large damaged structures in terms of medium-sized infrastructure facilities. This is the fishing port at Amoy. We could see that the tsunami washed out basically one section of the port, which is highlighted here in red. And something to kind of give you a magnitude of the effects or how big the waves are. This is a 12-meter structure. That's a Toyota Highlander. Oh, no, it's a Land Cruiser Prado, I think. So that's about 2 meters. This is about 6 of those, about 12 meters. You could see some debris on the top. So that's how we kind of determined that pretty much the wave there was surpassing the 12-meter mark, which is around 36 to 40 feet. The objectives of our work is to develop deterministic and probabilistic seismic and tsunami multi-hazard analysis on open-type wharfs. This is the joint effort with the Cascadia COPES Hub. For this presentation, we will focus on developing the models of tsunami structure interaction for the open-type wharfs in tsunami inflow stage, and we are also going to talk about characterizing the structural response to the cascading seismic and tsunami loads. Hopefully at the end of this research project, we will be able to provide recommendations for the design of open-type wharfs that are in tsunami-prone regions. If we talk about hazards and demands, currently ASCE 61 is the code that specifies the seismic demands for open-type wharfs, and we basically relate this to forces and drifts from our earthquake. However, for tsunami, it's kind of a gray area because there's the energy grade line method from ASCE 7, but other than that, there's no codified based approach to compute these demands. So you could take it on your own way and do it deterministically, but it's kind of difficult from the consultancy side. So another hazard or demand that we are interested in looking at is the scouring effects on the foundations. This might or might not be real. We'll figure it out as we work on it. So this is some of the amazing work that's being done by the Cascadia COPS Hub, and I like to highlight that they are using 52 scenarios for ruptures in the Cascadia subduction zone. They use a logic tree to compute basically the earthquake and the corresponding output ground shakings. We'll take just 1 second to look at the animation from the beginning. It's starting right now. And we get the corresponding tsunami. So all of this gives us a better understanding of the time-dependent cascading hazard associated with these events. And it's quite important. Oh, there you can see some effects of the tsunami. Well, we are leveraging this data and using this as input for our different models. So in terms of our workflow, we take the Cascadia subduction zone rupture scenarios. Their outputs are based on acceleration time series at the bedrock and some displacement time series at the bedrock also. We take the acceleration time series and we perform a site response analysis, which will be our step 1 for our sequential earthquake tsunami soil structure interaction model. And alongside, University of Washington is developing some inundation models. Thanks, Tsunami model is from University of Washington. And they propagate this from deep waters to the coast, and they provide us with flow velocities and flow depths. We use that to feed our wave impact model that's based on smooth particle hydrodynamics. And from there, we obtain pressure time series for our next step in our sequential earthquake tsunami model. So to convince you that our numerical modeling has a good way of representing the physics and the hydrodynamics, we have used this physical modeling in which they placed a scaled 1 to 10 elevated 2-story structure in the wave flume, in the large wave flume at Hinsdale Wave Research Lab at Oregon State University. They instrumented the front face of the structure with pressure gauges, and throughout the wave flume there's instrumentation for resurface elevation, close to the wave generation, close to the structure. There's also some velocity sensors all around the flume. And to talk a bit about how we are doing this numerically, we use smoothened particle hydrodynamics, which consist in taking a continuum system such as a fluid and discretizing it on a particle-based discretization. We use a Lagrangian Navier-Stokes SPH-based scheme in which we take the momentum conservation, the mass conservation, and the energy conservation equations to solve with the kernel-based solution, which actually means using a weighted average for each particle, and everything in the support is part of the weighted average computation. There we obtain the hydrodynamic quantities of interest, and that's how we determine what's going on with the flow. There's a big assumption that we make is that the fluid is weakly compressible, and this gives us a very big benefit in terms of computational costs, and that's where we introduce Tight's equation of state for the solution. This is one of the cool outputs of the simulations from SPH. You can see here a broken wave impacting our, I'm going to repeat that, our broken wave impacting our elevated structure in the large wave flume. The colors represent the velocity of the particles, and it is worth mentioning that for 1 second there's 20 frames for it, so this is kind of sped up. For validating our model, we compare free surface elevations throughout the close to the wave generation, after the 2 sets of slopes, and after the structure. So we can see that we get a pretty accurate prediction with both cases in front of the structure and after the structure, as well as pretty close to the wave generation. We also look into the pressure fields, in which we noticed an effect of asymmetry in the experimental results, where we could see larger pressures developing on one side of the structure. So this site kind of developed a bit cases or trials with larger pressures, but however, on the right side, on this side basically, we were able to match pretty much the averages of the pressure fields. We also conducted a sensitivity analysis in which we used a Morris analysis to use the effects of nonlinearities in between these non-physical parameters that we varied, and determined that even though that the response changes, we are plotting here the relative root mean square error for resurface elevations and pressure time series. So we could determine that even though we vary the parameters on this table, we don't see a big influence in the response of our quantities of interest. To talk about our application example, we are locating an open-type warp structure in Newport, Oregon at Yakina Bay. Since we have some amazing site data that was courtesy from GRI, we have some shear wave velocity borehole logging, some CPT reports, and some SPT reports to complement that. In terms of our structure, we have placed this very large wharf, but we're actually just analyzing this very small portion of it, since we can assume that in the longitudinal direction, it's very stiff, and we could actually capture the effects on the short side. And this is what we've done in terms of our SPH models and our OpenSeas models. So in terms of our site response analysis, we use deep soil 1D analysis, in which we propagated basically the acceleration time series we got from the models from USGS, and we threw it up through our layers. We obtained a response, and here in the black line you could see the response spectrum from the input. There's one response at 75 feet. That's where we believe that our piles are going to be located. Well, it's basically dependent on the service loads, so we might vary that too to study that influence of that. And the spectral acceleration at the ground surface. In terms of our wave impact model, there's 52 scenarios from the inundation models that's developed in GeoClaw. From those 52 scenarios, there are some representative cases, such as this specific case, the buried locking STR-10 deep, in which we have the free surface elevation. This is a time series for about 240 minutes, actually. I'm just showing you the first 120 minutes. And we also have our velocity through the same time series. This is a depth average velocity. So we use this as input for our SPH models. And using the open boundary condition, we generate the forces and pressures for this model that you will actually see here. Here you're going to see the horizontal pressures on the piles. This is just the measurement at the middle of the piles. And this is measurements of pressures at the bottom of the slabs. So we want to capture mostly anything that we can get from the models. So this is how the structure would look into the measurement of the wave incoming from right to left. And this is the pressure at 14.8 seconds, which actually represents the largest forces in the structure. Something interesting that we found is that maximum pressure is not exactly at the same time as maximum forces. So it's a cool fact that we found out. Oh, my bad. And this is the maximum pressure time series profiles for the set of piles of the structure. For our OpenSeas model, we will introduce our soil mesh. We will connect them with PY, TZ, and QZ springs to get some interaction with our piles. This is pretty much what's done in Caramonte's paper from 2013. And we will just extend that, basically introducing the tsunami loadings. In terms of materials, we're using elastic, pressure-independent multi-yield, and pressure-dependent multi-yield material. For our piles and girders, we're planning on using, our current step is using elastic beam columns, and we will later move on to fiber force-based beam column elements. So from this, as I mentioned, we will include the tsunami pressures and get the whole set of tsunami soil structure interaction. And to summarize what's been done so far, we have validated our SPH models for broken waves, for an unbroken wave, and a sensitivity analysis. And our application example, there's a big thing that we should mention, that For our full scale, we're using a rigid structure, so there's basically no structure interaction for our smoothing particle hydrodynamics. And in terms of future and current work, as I mentioned, there are some cases from the tsunamis that actually do not generate a wave impact in our structure due to the protections that have been placed in the Newport and Yaquina Bay. So we have to define which are the ones that we are actually going to use, so we could use the corresponding ground motions. And in terms of our cascading seismic tsunami modeling, we will apply the pressure time series that we get from the software called Dual S Physics. And that's what I've been using to model this. And apply it on nonlinear open seas model. And from all of this, we want to assess the damage states of the structure to check if we're actually complying with what ASC 61 says, since it's the only guidance towards performance in these type of structures. These are some of the reference, and I would like to answer any questions you might have, or try at least.